In this video, we're going to talk about hydrates. And the reason we're picking hydrates to learn right now is because, well, for one reason, they're very common. Most of the chemicals that you use in class are actually hydrated forms of those ionic salts. When I buy chemicals from the chemical supplier, most of the time I have to buy hydrates. And if I want to use the chemical, like for example, you see on the screen here, cobalt 2 chloride monohydrate. If I wanted to use just cobalt 2 chloride, then I would have to prepare this compound for use by heating it up first. The hydrates are usually cheaper because they do have the waters caught up in the structure. So as a chemist, you need to be familiar with hydrates. Now, for a more practical reason of why we're choosing this moment to learn about them, the naming system of hydrates incorporates everything you've learned about ionic that we just got finished learning about. Additionally, we're going to be learning about the covalent naming system in the next unit. Hydrate naming system actually incorporates a little bit of the covalent naming system as well. So it's an excellent bridge for you to keep practicing your ionic naming, and then let's add the prefixes of the covalent naming, and by the time we get to that in the next unit, it'll be super easy for you. So let's begin and go through some hydrates. One of the things you'll notice on the first slide here is how colorful these hydrates are. And the reason they're so colorful is that the water molecules that get caught up in the lattice of these ionic salts are going to interact with light in different ways. We all know that water is quite sparkly, like we think of the blue ocean and how water interacts with light. So it's all a result of the water being in the lattice structure. So what is a hydrate? A hydrate is an ionic compound where water is caught up in the crystal structure. These water molecules can attach through intermolecular forces that we'll learn about soon. And that attraction would be like through ion dipole type forces. If you look over here on the middle right of your screen, I have a barium cation here, and we can see above that a water molecule is being attached to it. This is illustrating an ion dipole interaction from a full charged cation to a partially charged, fractional charge oxygen from the water. The waters can also be attached through complex ion formation where it becomes a ligand. And now a ligand is just something that, gosh, what's the easiest way to say it? It's just an appendage. That's all it does. It just comes in and sticks to, in this case, the copper, or whatever the central metal may be. I used to use, when I taught Mississippi, the analogy of a tick on a dog. I mean, it just comes in and sticks to it. The opposite of a hydrate is called an anhydrate. So the last bullet there, compounds that have all the water removed are called anhydrous. Okay, so you will see those two words from time to time when you're reading problems. If you ever see anhydrated or anhydrous, that means it's just the plain ionic compound. You've already learned how to name anhydrous stuff. That's what we did in ionic bonding. Okay, so hydrates are really stable. That's why they form in the first place most of the time. And they do so by sucking up water out of the atmosphere. Well, that's at least the minimum. They could suck up water from anywhere, but they do it usually from water in the atmosphere. So we have some terms here that help us describe hydrate behavior. If an ionic compound or a hydrate is efflorescent, it spontaneously loses water to the atmosphere, and that's a little unusual. Normally that doesn't happen because the hydrates are pretty stable. Let's watch a quick video with an example of a hydrate. Let me show you how easy it is to remove the water.
Focus on the different types of hydrates. Here we have an example of a hydrate. It's copper 2 sulfate pentahydrate. That means there are 5 water molecules contained in this crystal structure of copper 2 sulfate. So you can see that the copper 2 sulfate pentahydrate is being heated. And as it loses water from the heating, it becomes copper 2 sulfate and 5 water molecules released as vapor.
Notice the water
now the
droplets.
copper 2 sulfate that you can see has changed color is referred to as the anhydrous salt, meaning the water has been removed from this salt.
You can see in the video the blue copper 2 sulfate pentahydrate, as it was heated, the water molecules were released, and then we have a color change here. That's a clue of a chemical reaction. It's sort of a chemical reaction because the water molecules are caught up in the lattice, so you're breaking up that. But you're just going to the anhydrous form. But notice up here the water droplets forming at the mouth of the test tube. So there's your proof that water's being driven off.
Now, as you can see in the video, if I add water back to this anhydrous salt, I can reverse this process and get the original hydrate over here restored. And you can see the color comes back to it.
And that's a good illustration of how easy it is for hydrates to form. Just a little water and you're almost back to square one with the copper 2 sulfate pentahydrate. The next terms I want to go over with you are sort of the same: hygroscopic and deliquescent. Hygroscopic means that it will absorb water from the air, and that's what most of these hydrates will do. Hygroscopic is a very general term. It doesn't really talk to you about how much it can, just whether it can or not absorb water. Deliquescent is a much more specific term. Deliquescent implies that you really soak up water a lot, and in fact you can absorb enough so that you can start dissolving yourself. So let's watch a quick video with a time lapse where you can see that process happening.
Many chemical compounds have the ability to absorb water directly from the air and form stable hydrates. These compounds are known as hygroscopic. Some compounds are so hygroscopic that they will absorb enough moisture to dissolve themselves. Here, shown with time-lapse photography, sodium hydroxide pellets absorb moisture directly from the air. This process of self-dissolving is called deliquescence.
So as you can see from that video, these hydrates, or these, I guess this would be an anhydrate form, has a real strong potential to form the hydrates, and they can actually dissolve themselves. As we go through the year, we're going to be using that chemical you just saw, sodium hydroxide, from time to time. That's why it's very important you never leave the top off of the container. And I'll probably yell at most of you at some time in the spring semester because you leave the top off my sodium hydroxide. Don't let that be you. Let's move on to the naming system. The naming system, as I mentioned, is a bridge between ionic and covalent. The first thing you do, here's our example, PB, and then we have C2H3O2, two of them, and then dot 3H2O. So there's 3 waters attached for every one of these molecules. To name it, look at the first bullet. First word is the name of the anhydrous ionic compound. In other words, just use your ionic naming rules like you just learned to name the anhydrous part, the part on the left of the dot. So if we look at this, we have Pb, which is lead, and we have this ion here, acetate. Remember, lead needs a Roman numeral. We need 2 of these acetates, so that means we have lead 2 acetate. So that's the anhydrous part on the left of the dot. To acknowledge the water, we're going to use the word hydrate. Hydrate, you know, when many of you hear that word, you think of water anyway. So that's how we do it. And what we're going to do is put a prefix in front of hydrate to just say how many waters there are. 3 is tri, so we're going to have a trihydrate here. To finally put everything together, the full name of this hydrated compound is called lead 2 acetate trihydrate. So that's not too hard at all. Probably the hardest part of this is the ionic stuff, which you've already learned. So not that bad at all. We're going to have some practice for you to work on. So make sure you do that practice and become a master at this. before I leave that, these prefixes are the ones that we're going to need to know for covalent naming pretty soon, here in the next few weeks anyway. All right, so here's some more practice. I'm going to let you try to name these, and then we'll scroll up and see the answer. So let's start with Li2SO4, and then 10 waters. Hopefully you have named that as lithium sulfate decahydrate. All right, the next bullet, we have our PB back. What is the Roman numeral this time? If you said 4, you're right. This is lead 4 hydroxide. 7 is heptahydrate. All right, one more from the formula. We have cesium. Oh, this is a typo. This should be CO3. So we're going to have cesium. Well, actually, I didn't make a typo. I made up something. I don't know if that's really true or not. So I was banking on here CO3 is carbonate, so CO2 will be carbonite. I don't know if that's really true or not. Cesium carbonate dihydrate. The important thing here is, did you get the dihydrate part? All right, in the bottom part, we're going to turn it around and go from words into symbols. So vanadium 3 bromide. Vanadium is a transition metal, V+3. Bromide is Br-1. And then what does tetra mean? Right, it means 4. So we're going to have VBr3 for the vanadium 3 bromide, and then 4 waters. Strontium nitrate. Many of you could probably put that together. How many nitrates would I need for strontium? That's the thing to figure out. The answer is 2. So you're going to have SrNO3 2. Penta is 5, so 5 waters. And then finally, calcium carbonate trihydrate. Calcium is +2, carbonate is -2, so they're going to go right together, and then tri is 3. So there is your calcium carbonate trihydrate. All right, the final thing we're going to do with hydrates in this introductory video is talk about percent water. In this unit, we're learning about percent composition, which is a percent by mass of all the elements that make up a compound. So the same idea here, but we call it percent hydration because we specifically want to know how much water. What's the percent of water by mass in these hydrates? It's a very common sense problem. If you want to find a percent, you need to know two things. You need to know how much the part is, in this case water, and you need to know how much the whole thing is, in this case the entire hydrate. So what we're going to do is find the molar mass of the entire thing. Okay, the formula mass, molar mass, whichever. This is ionic, so that's why we call it formula mass. So here is the mass calculations for all that. We have 1 copper, so here's the mass of 1 copper, 1 sulfur, and then the 4 oxygens. So the mass of the anhydrate part is 159.62. Let's now count for the waters. There's 2 hydrogens, there's 1 oxygen, so the mass of just 1 water is 18.02. Okay, that's just 1 water. Now to get the total mass, we're going to take the anhydrate, 159.62, multiply the water times 5 and get almost 250, 249.72. So that's the whole. Now we need the part. And what we're going to do is divide the mass of water in 1 mole of the hydrate by the total. So 5 times 18, that's how much water we have, is 90.10. That's where that number came from, 90.10. Divide that by the whole thing. The 100 is multiplying the number, the quotient there by 100 in order to make it a percent. So this particular compound is 36.08% by mass water. We're going to do a lab where you're going to make this calculation again on your own. Also in our lab, we're going to use the empirical formula process to figure out how many waters there are. And so it's very important you understand hydrates, because we're going to use hydrates to practice some of our compound stoichiometry, specifically percent composition and empirical formula. So if you have any questions, make sure to come by and ask.